Hello and welcome back to the chemistry video series for Chem 141. Today we're going to be talking about strong and weak electrolytes. So the first thing that you need to know is where the name electrolyte came from. So essentially, when you dissolve an electrolyte in water, the water should then be able to conduct electricity. And the strong, weak, and non-electrolyte part of that tells you how well that water will conduct electricity after you put the electrolyte in. So there are some types of compounds that are strong electrolytes, weak electrolytes, and non-electrolytes. They're classified under those different compounds. So water by itself does not conduct any electricity. Pure water does not conduct any electricity. However, when you put electrolytes in that water, such as salt, then it becomes capable of conducting electricity. Okay? So the reason why you see this light bulb lit up here is because we have this strong electrolyte, NaCl, present in this solution. And that is that's what's causing the light bulb to light up, because there's electric current that's being able to transfer through this water from each of these two electrodes. However, if we take something that is not an electrolyte, such as ethanol, you can see that the light bulb does not light up at all because ethanol is classified as a non-electrolyte, okay? And then interestingly, with these other compounds over here, acetic acid, the acetate ion, and the hydronium ion, these are what's called weak electrolytes because they light up the light bulb a little bit, but not nearly as much as the strong electrolyte. So the main thing that you need to know is non-electrolytes are generally covalent compounds, okay? Meaning that they only contain covalent bonds. Whereas strong electrolytes and weak electrolytes can be, so these can be either, these can have ionic bonds, okay? And when you dissolve them in water, the water actually forms what's called a hydration shell around the ion, and it actually pulls the ionic bonds apart due to the polarities of the water. So it tears apart ionic bonds and separates the atoms into their individual ions. So an example of what that would look like is NaCl solid. When it gets put into water, it becomes Na plus aqueous now, because it's in aqueous solution, plus Cl minus, also aqueous. Okay, so that's an example of how a strong electrolyte can be converted into its ions when it's dissolved in a liquid such as water. And also, one more thing that I want you to know is that in this chapter, we're mostly going to be dissolving things in water, but you should also know that like dissolves like. So if something is a polar compound, meaning that it's ionic or it has polar bonds, polar covalent bonds, then it's going to dissolve in a polar solvent, such as water. But if it's nonpolar, meaning that it doesn't have ionic bonds, it only has nonpolar covalent bonds, that's going to dissolve in a nonpolar solvent, maybe like some kind of oil, for example. So the main thing you need to know, strong electrolytes dissociate completely, okay? Dissociate completely. While weak electrolytes only kind of dissociate like 1 to 2%. And these kinds of electrolytes have this thing called a Kd, which is called a dissociation constant. And this number basically tells you how much the electrolyte is going to dissociate. And this becomes especially important when you're dealing with things like weak acids and bases, which we'll get to later on. But non-electrolytes, again, they do not dissolve at all because they're entirely covalent. So that would be things like glucose, for example. Glucose, C6H12O6 only contains covalent bonds, so it's not going to be able to dissolve at all. All right. And one more thing I want to say is that sometimes with electrolytes, you have a number that is associated with each different type of electrolyte called I. And I is basically equal to the number of ions that a compound forms when it's dissolved. So for example, since NaCl, salt, dissolves into 2 ions upon dissociating, upon being dissolved, its I is equal to 2, okay? Because it forms 2 ions upon being dissolved. So, yeah. I think that's all I wanted to say about that. So I'll move on to the next slide. So this is the tricky part of this particular chapter, because in Gen Chem you have to you just kind of have to memorize what compounds are soluble and insoluble or slightly soluble. So not all ionic compounds are going to be electrolytes. Some will be insoluble, okay? And essentially you'll just have to go through this chart and kind of memorize it and see what's going to be soluble, insoluble, and slightly soluble, okay? And you also have lab experiments associated with this kind of thing, all right? So next, I just want to give you some quick little problems that we can talk about how to go over, like strong electrolyte and weak electrolyte problems. Okay, so let's just say you have a solution of 100 milliliters of water, and you're dissolving 0.1 moles of KOH in that water. Okay. Now let's just say the problem wants us to figure out the molarity of that. Okay. So if going off of the molarity videos that we produced in the past, I'll let you pause the video and try to figure out what the molarity is. Okay. So if you, hopefully you've figured out the molarity, and the way that you would do that is you would take the molarity equals the moles divided by the liters of the solvent, or sorry, of the total solution. So the molarity here would be 0.1 moles divided by however many liters there are. And since we have 100 milliliters of water, we have 0.1 liters. So our molarity is just 1. Okay. Now, what do you think would happen if I decided to add, let's just say, another 100 milliliters of water? How do you think it would change the molarity? Would it increase? Would it decrease? How would it be affected? So I'll give you another chance to pause the video and figure that out, what the new molarity would be. Figure that out for yourself. Okay, so the way that you would calculate that, the number of moles doesn't change because we're not adding any more KOH. So the numerator number of moles is going to remain the same. However, the denominator, we increased by another 100 milliliters of water. So we're essentially doubling it here. So the denominator here is going to change from 0.1 liters to 0.2 liters. Okay. And now our molarity is 1/2. All right. Now, what do you think? Do you think the amount of moles changed as a result of diluting this solution that way? Well, hopefully you answered no, because the number of moles will always remain the same unless you add more KOH. So the number of moles remains 0.1 moles in this situation. Okay, and KOH again is a strong electrolyte. So it's going to dissociate completely. All right. If we were dealing with a weak electrolyte, this problem would become a little bit more difficult because we wouldn't exactly know how much the compound is dissociating or not. We'd have to figure out what the dissociation constant is before we make that decision. And we'll get to some problems later on with titrations and weak acids and weak bases where we'll have to do things like that. But for now, this is the end of this video. Thank you for watching.